Hi everybody, and welcome to a video on a continuation of section 16.3. So we began section 16.3 on Wednesday, and since I'm unable to be with you on Friday, you are watching this video to finish section 16.3 for Friday. As I said in class on Wednesday, I hope that you will show up to class on Friday for extra credit to work on problems over this material. I hope that will be enlightening for you to do that and helpful for you. If this material confuses you in any way, you need to email me or ask me about it on Monday. So in this video, I'm going to finish up section 16.3 by doing three things. I'm going to talk about legitimate ways to assign probabilities to things. I'm going to talk about a concept called complementary probability. This is sort of a cute sort of trick to compute certain probabilities, a sort of backdoor way. You can sort of do a sneaky little trick. And I'm going to show you some more examples of computing probabilities. So that's what we're going to do. So here are a few things to note at the beginning about legitimate ways of assigning probabilities. If E is any collection of outcomes, like you draw a king when you draw a card out of a 52 card deck, whatever E happens to stand for, the probability of that event occurring is 0 or bigger. Okay, so probabilities are always positive or 0. Probabilities are never negative. And by the same token, if E is any event, then the probability of E is at most 1. That's what this is saying. You cannot have a probability bigger than 1. So probabilities must be 0 or bigger, and also 1 or smaller. You can't have a probability of 1.5 or 17. You also cannot have a probability of -2. So all I'm really saying here is, when you give me the probability of something occurring, it's either a percentage between 0% and 100%, if you want to talk in terms of percentages, or it's a number between 0 and 1. Whichever way you want to think about it. This is a true statement. You can't have probabilities less than 0%. You can't have probabilities bigger than 100%. Both of those are impossible. In particular, if you think about the boundary of this range, they have to live between 0 and 1. If you tell me the probability of E is 0, then what you're really saying is that E is impossible. Okay, there's no way for E to occur. So think about rolling 2 dice and seeing a sum of 1. That is impossible. The sum of 2 dice is at least 2. So the probability of rolling a sum of 1 is 0. And on the other hand, if probability of E is 1, or probability of E is 100%, whichever way you want to say it, then what you're saying is that E is guaranteed to happen. It is a certainty that E will occur. So think about the probability of rolling 2 dice and the sum of the faces being at least 2. Okay, that's going to happen no matter what, right? If you roll those 2 dice, you're going to see something that's 2 or bigger. So the probability of seeing something that's 2 or bigger is 1. It is a guaranteed certainty that that will happen. So if on your exam, or whenever, you compute a probability and you get a number like 3, what you're essentially saying is that you're extra certain. You're even more certain than certain. Okay, so you're giving a number that's like certainty times 3 or something, which doesn't mean anything. Okay, that's a meaningless number. And if you give a number like -2, you're saying that your probability is like even more impossible than impossible, which is also meaningless. Okay, so any answer you give must be between 0% and 100%, or between 0 and 1, depending on whether you want to give me a percentage or not. Okay, so consider this question here. This is a question about legitimate ways of assigning probabilities to things. So suppose you have a loaded 4-sided die. Okay, so it's been tampered with. For this particular die, I'm going to tell you that the probability of rolling a 1 is 30%, or 0.3. The probability of rolling a 2 is 25%, or 0.25. The probability of rolling a 4 is 35%. So the question is, what's the probability of rolling a 3? Well, some of you can answer this question with no problem, but let's talk through the logic of what's happening here. When you roll this die, you are either going to see a 1, 2, a 3, or a 4. Those are all of the options, right? It's a four-sided die. You're not going to see a 5, you're not going to see a 7, whatever. So 1, 2, 3, and 4, those are the 4 possible outcomes. And furthermore, those 4 outcomes exhaust all of the potential probabilities. So there's a 30% chance of rolling a 1, there's a 25% chance of rolling a 2. So those two combined probabilities are 55%. So the outcomes of 1 and 2 take up 55% worth of what's going to happen. And then the probability of rolling a 4 is 35%. Well, 0.3 plus 0.25 plus 0.35, that's 90%. So these 3 outcomes by themselves take up 90% of the probability. So what's left for rolling a 3? Well, what's left is 10%. So the probability of rolling a 1 is 30%, and the probability of rolling a 2 is 0.25. The probability of rolling a 4 is 0.35. So if you add up the probabilities of the individual outcomes, you must get 100%. Okay, so this is always true. So if you have a sample space that consists of these outcomes, if you add up individual outcomes, so just rolling a 1, rolling a 2, whatever, flipping a heads, flipping a tails, whatever your individual outcomes are, if S consists of those outcomes, then the probabilities of the individual outcomes must add up to 100%. Okay? No more, no less. If you add up to more than 100%, you have too much probability there. Right? It doesn't make sense to have a probability of 105%. But if they don't add up to 100%, then you have some missing probability. Because that doesn't make any sense to have to exhaust the probability and only have 90% worth of it sitting there. So this is useful in your homework. There are a couple questions like this in your homework. They give you some probabilities and they say, hey, what's the probability of this other thing happening? And you just have to recognize that the probability of everything combined has to be 100%. So keep this in mind when you do your homework. Okay, so let's now move on to complementary probability. So here's the idea. Let's let E be any event. Okay, suppose you're, then this equation is true. The probability that E occurs plus the probability that E doesn't occur is 100%. Okay, so what is this saying? Either E happens or it doesn't. Those two outcomes are mutually exclusive and they eat up the entire sample space, right? Either you're inside of E or you're not. Either E happens or it doesn't. Those are only two options. So if you look at the individual probabilities of both of those guys, you've exhausted all the possibilities, right? Every outcome is either in E or not in E. So all this is really saying is E happening, E not happening, those two events by themselves take up the entire sample space. So when you add the probabilities together, you get 100%. So think about in terms of flipping a coin, right? Let's let E be the event that you flip a heads. Then E not happening is flipping a tails. You either flip a head or a tails, right? There are no other options. And the probability of flipping a heads plus the probability of flipping a tails certainly is 100%. Okay. The complementary probability rule is this equation right here. So if this first equation is true, P of E plus P of not E is 1, you can just move the P of not E over to the other side and you get this. The probability that E happens is equal to 1 minus the probability that E does not happen. Okay, so you might have a few questions about this, but one question that arises immediately to me is, okay, I accept that this equation is true, but so what? You know, why would I care about this? The reason you care is that you're asked to calculate probabilities of things, right? That's what your homework is. Calculate the probability of this, calculate the probability of that, etc. Well, maybe computing that direct probability is difficult, right? Maybe you stare at that and you think, man, I really don't know how to count what I'm supposed to be counting here. You know, I just don't know what to do. If that's the case, it might actually be way easier to calculate the probability that this event doesn't happen. So you can sort of think about computing the probability of the opposite. If you can calculate that probability, the probability that the event doesn't happen, then all you have to do now is do 1 minus that number, and you will get the probability that you are interested in. Okay, so we're going to do an example in a second, but again, the global picture of what's going on here is you want to calculate probability of something occurring. Maybe that's difficult. So what you do instead is calculate the probability that this event doesn't happen. If you can get that number, then all you have to do is 1 minus that number, and you will get the probability you are interested in, this guy right here. Okay, so let's look at an example where this happens. So here's the rule again. Okay, so just consider this question. You're dealt a 5-card hand of cards, right? What is the probability that that hand contains at least one king? Okay, so let's think about how we might approach this. Well, first of all, the universe of this problem is 5-card hands, right? So if you're thinking about what are the possible outcomes here, you know, what could possibly happen? You're talking about all possible 5-card hands being dealt to you. So one possible outcome is the ace, 2, 3, 4, 5 of hearts. Another possibility is the ace of clubs, 2 of spades, 3 of hearts, jack of clubs, queen of clubs, or something, right? Those guys are all the possible outcomes. All of the possible 5-card hands are the possible outcomes. Well, how many 5-card hands are there? Well, you're taking 5 things from 52 things, and the order doesn't matter. So there are 52 choose 5 5-card hands, right? You're taking 5 cards from 52 cards in such a way that the order does not matter. So there's the answer to that, to just the size of the sample space here, right? Your sample space, or your overall universe, is all of the possible 5-card hands. There's that count. Okay, so this question that we're interested in, though, now we have to think about, man, how many hands are there with at least one king inside of them? Okay, there are 52 choose 5 overall hands, but how many hands only contain at least one king? So to answer this question directly, you would have to count that. You'd have to count the number of 5-card hands with at least one king, and then divide that by the size of the sample space, by this 52 choose 5 number. So you might want to give this some thought, but suppose you had to count the number of 5-card hands with at least one king. That is not a trivial exercise. One thing you could do is count the number of hands with exactly one king, exactly 2 kings, exactly 3 kings, and exactly 4 kings. Right? You could break it into those 4 cases and then add those all up. So if you have at least one king, that's the same thing as adding this number of exactly 1 king to exactly 2 kings to exactly 3 kings to exactly 4 kings. But it's actually really not that easy to count. So you can do it. I mean, you have the tools to do it. But it is not easy to count the number of 5-card hands with exactly 2 kings. It's sort of time consuming, and you have to really be careful. You have to make sure you don't double count things. So for example, if you're trying to count the number of hands with one king in them, suppose you have a hand with the king of clubs and the king of spades in it, right? That hand has a king in it. So you might count that hand as a success for this scenario, having one king. But then when you move on to having 2 kings, you don't want to count that again. Okay, so what I'm saying here is this problem right here of counting all this has all sorts of potential for error. It's hard, right? You might end up double counting, triple counting different hands, etc. So doing this directly is difficult. So let's use the idea of complementary probability to attack this problem in an easier fashion. So this is hard. Okay, so I'll just tell you that. You can do it. All of you have the tools to, but it's difficult. Okay, so let's let E be the event that your hand has at least one king. Well, this is the complementary probability rule right here. So the probability that your hand has at least one king is 100% minus the probability your hand doesn't have at least one king. Well, what's that saying? That's saying the probability that you have at least one king is 1 minus the probability your hand has no kings. Right? So the opposite of having at least one king is having 0 kings. You have no kings inside your hand. So what we're going to do now is we're going to compute this probability. And once we know this probability, we just do 1 minus and we will get the probability that we are interested in. Okay, so let's walk through that. To calculate the probability that your hand has no kings, we're going to count the number of 5-card hands with no kings. Okay? Now you should probably think about how you might do this, but let me walk you through the logic of this. Imagine counting the number of 5-card hands without kings. You can think of that as just choosing 5 cards from a set of 48 cards now. Okay, there are 52 cards total, right? But if you're assuming that you get no kings, that's as if you are taking the 4 kings out of the deck and then taking your 5 cards. So the number of ways to get, the number of 5-card hands you can get with no kings in them is just, okay, kick those 4 kings out of the deck. Now you have 48 cards left, and you want to choose 5 from that. So here is the number of 5-card hands with no kings. Okay, but once we have that number, we can now do probability your hand contains no kings is the number of hands with no kings divided by the total number of hands, right here, 52, choose 5, and if you ask your calculator what this is, you'll get about 66%. Okay, but this number right here isn't what we're interested in. We were interested in you get at least 1 king. But once you have this 66% number, all you do is 1 minus that number, so 1 minus 0.659, and you get 0.341. So what you've learned is the probability of having at least 1 king inside of your hand is 34%. And you got that number by considering the opposite outcome, the outcome that your hand had no kings. You computed that probability, did 1 minus that, and that got you to your final answer. Okay, so keep this concept in mind when you're doing your homework and when you're doing the group work problems on Friday. If you find yourself stuck, like, man, I really just can't compute this probability, I don't know what to do. One thing you can try doing is computing the probability of the opposite event and seeing if you can handle that. If you can handle the probability of the opposite event, then you get that number, do 1 minus, and then you are done. Okay, so that's the idea of complementary probability, and that is now the end of section 16.3. If anything in here confused you, if the problems on Friday confuse you, that's perfectly fine. Just make sure you send me an email or ask me about it on Monday or during my office hours or whenever. So, see you on Monday.